All right, well, welcome back. So in the previous lesson, we had a look at the parametric equations section, where we had a look at how a ordered pair, let's say you have a pair x and y, if x is a function of t and y is also a function of t, meaning that we have x being xt and y being yt, then we could write, so we can find the graph of it based on t. So it's a function of t, but we still have the x and y. So it's more like the composition of functions in this case. But so that we also had to look at some calculus involved with parametric equations. So we had to look at the area, we had to look at the um, arc length, and we also had to look at the surface area as well. So in this lesson, we will be having a look at the polar coordinate section. So another way to express the polar coordinates is to use the polar coordinate system, which uses an angle and the distance from the origin, or which sometimes we call the pole. So we had a look at polar coordinates previously a little bit when we talked about the complex numbers, when we talked about the polar form of complex numbers, which uses in the same values, which we have the r being the distance, and we have the theta being the argument of the complex number. So the same thing can basically be applied to polar coordinates in this case as well. So let us have a look at this first example. So let us first plot the following points. We have, first of all, 3 and pi over 3. So what does that mean? In the polar coordinate system, we're always going to have an ordered pair that is of the form r and theta. So that is the polar coordinate. So if we were to put this on the plot over here, we would have to come to the standard angle and standard position first, which is here. This is going to be 3 here, which is the starting point. And we're going to go in a counterclockwise direction because the theta here is positive. And we're going to go until the pi over 3. So we're going to rotate to here. That is your first point A. We do the same thing for B, where we have 2 and negative 3 pi divided by 4. But whenever we have negative, we go in a clockwise direction. So we're starting at 2, and we're going to go 3 pi divided by 4 in a clockwise direction, which is, oh, we went a bit over, which is until here. So it's going to be, so here's 2, and here is 3 pi divided by 4, this point here. Okay. And as for, so that's point B. For C, since we have a negative r this time, we're going to go 3 units to the left as the starting point. So we're starting here. So this point is going to be negative 3. And we're still going to go in a counterclockwise direction because theta is positive. So we're going to go until 4 pi over 3. So it's going to be this point over here. And if we plot the last one, notice that, well, 7 pi divided by 3 is the same as saying 2 pi plus pi divided by 3. So that means we're going to go 1 full rotation from standard position. And that means that little extra pi over 3, we're going to rotate it to here. So 1.5 is about over here. So we're going to rotate to pi over 3, which is this part. This is D. So that is how you use the polar coordinate system. All right. So a pair represented by r and theta can be put on a Cartesian coordinate system. So this is when we talk back in complex numbers, where if we have a point, so say this is your x and y, this is your point here, x and y, And if you draw a line that connects it, you form a triangle, where this time, so this is your x, and this is your y. Now, in order to find this distance, which we usually call r, we use Pythagorean theorem. R here, if you recall, is the x squared plus y squared, which is the modulus of a complex number. And as for the argument, or the theta here, it's the angle from this line over here to the x-axis, which is this line over positive x-axis. So this is your gonna be your theta here. Usually, we can use tan inverse of y divided by x. Now remember that the trig ratios for sine and cosine can be written as sine theta, which is equal to y divided by r, and cos theta, which could be written as x divided by r. So we can come up with expressions for x and y in terms of these polar quantities. So if we move the r to the other side, what we get is that, well, x here is going to be r cos theta, and y here is going to be r sine theta. And so that means if x and y are our Cartesian coordinates, we can transform these into the polar coordinate. So this is going to be r cos theta, r sine theta, like that. So we could change them from time to time, which is nice. Okay, so let us have a look at some examples of how to convert from polar coordinates to Cartesian coordinates. I'll leave these two as an exercise here. So this is exercise and exercise. So we'll be having a look at the first and the third one, so A and C. So in order to convert to Cartesian coordinates, remembering that x would correspond to the r cos theta, the y would correspond to the r sine theta. So we would have to put the r and the theta into each of these parts over here. Since we have r is 3 and theta being pi over 3, then our x coordinate is going to be 3 cosine of pi divided by 3, which is going to be 3/2. And for the y, we have 3 sine theta, which is pi over 3. And that would give you 3 root 2 divided by 2, or 3 root 3 divided by 2. And same thing for part C, but this time we have a negative r value. So we do the same thing. So x here is then negative 3 cos pi over 3, which then gives you the negative values. So this is going to be negative 3/2. And the y value, same thing, negative 3 sine pi over 3, which is negative 3 root 3 divided by 2. And that is how you convert to Cartesian coordinates. So we're going to we were going from r theta, and we're transforming it to an x, y coordinate pair. So let us do the same thing, or the opposite way, where we convert Cartesian coordinates to polar coordinates. And once again, I'll leave B and D as an exercise. And we will do A and C. So for the first one, for the r, we want to find r and theta at this time. So the r formula we know, which is going to be by Pythagorean theorem, is the square root of x squared plus y squared. So for the r, we use Pythagorean theorem. So it's 3 squared plus 4 squared, which is going to be square root of 25, which is just going to be 5 then. Then theta here, which is the tan inverse of y divided by x, or 4 divided by 3. And it lies in quadrant 1. So that is going to be approximately about 0.93 radians. So this is your r, this is your theta here. Okay, so let's have a look at the second one, or part C. So we do the same thing. We use Pythagorean theorem. So we have -2 squared plus -2 squared. But this one here is going to be the same as saying 2 root 2. So that's going to be your radius. And our theta here is going to be the tan inverse of -2 divided by -2. But since both x and y are negative, the angle theta has to lie in quadrant 3. So because this lies in quadrant 3, this is going to be 5 pi divided by 4. And that is going to be your r and theta. All right. So we can also graph polar equations of the form r is equal to f theta or f of r theta by finding all the points that satisfy the equation. For example, let us try to graph r is equal to 2. So for this equation, remembering that r is equal to the square root of x squared plus y squared. So if we transform this, r is equal to 2. That's going to be 2 squared x squared plus y squared. Now this equation should look familiar because it's just the equation of a circle of radius 2. So this on a graph, it'll look something like this. So that's your circle. You have a radius of 2. So it's the equation of a circle of radius 2. Okay. Now, if you want to see this a little bit cleaner, or using the x and y polar coordinates, so using these two, observe that while x is equal to r cos theta, or 2 cos theta then, and y is equal to 2 sine theta. Well, x squared plus y squared is going to equal to 4 cos squared theta plus 4 sine squared theta, which then we know is equal to the radius, which is equal to 2 squared. And so after that, we know that this is going to equal to 1 because cos squared plus sine squared, they have the same coefficients as well. So that's going to equal to 1. Multiply that by the 4, and you get 4 squared. So all these here are equivalent to each other. And so we should get an equation of a circle of radius 2. As for the next one, let's have a look at theta equal to 1. Let's try to graph this. Well, one thing that we know is that tan inverse is usually written as y divided by x, which is equal to tan theta here. But since theta we know is equal to 1, so we could change this to 1. So that means here, y divided by x, which is equal to tan of 1. And so we have y tan of 1x. Now this line should look a bit familiar because it's the equation of a line of slope 1, or slope tan of 1. That is the slope here. And graphically, if we have a line that's drawn like this. This is your theta, which is equal to 1 radian. Okay, so let's have a look at some sketching parts here. So say we want to graph the equation r is equal to 2 cos theta. Well, we're going to use a table of values, but in the previous lesson, we had a look at graphing parametric equations using 3 values, the t, the x, and the y. Now that we're dealing with polar coordinates, we're going to be using 4 values here, which are going to be theta, r, x, and y. The input value here is going to be our theta because your theta is going to be this, and the r, x, and y are going to be the outputs based on what we get. So let us create this table. And let us say we go from 0 to 2 pi. So that means on the table, we'll put down 0 until 2 pi, pi divided by 2. This is 3 pi divided by 2. This is pi over 4, 3 pi divided by 4, 5 pi divided by 4, and 7 pi divided by 4. So if we put the values into the equation, the values of theta, we will get a value of r in return. So the values that we should get is as follows. So we should get 2, square root 2, 0, square root 2, negative 2. Oh, there should be negative. And then the next set is going to be negative root 2, 0, root 2, then 2. So now once we have the r and the theta values, we can go ahead and put them into the x and y, which remember is r cos theta and r sine theta. So we could go ahead and put that in. And for the x coordinate, what we should get is 2, 1, 0, 1, 2, and then 1, 0, 1, 2. So that's the x coordinate that we should get. As for the y coordinate, we should get 0, 1, 0, negative 1, 0, 1, 0, negative 1, 0. So that is the y coordinate that we should get. So now that we have the x and the y coordinate, we can then put this on to the graph here, which we could graph. And so if we graph this, let's graph this. So say that this is our x-axis or the y-axis. This being our x-axis. We go, so say that this is 2. Here's 0. And this is 2 here. So 2 and 2. And this is 1 here. Now, whenever it's at 1, it can go between 1 and negative 1 for the y value, as we've seen. So basically what we should get as the graph looks like this, which is the equation of a circle of radius 1, but it's centered at 1, 0. So this is the equation of a circle radius 1 centered at the origin. All right. Sorry, not the origin, centered at 1, 0. Okay, so let us find the Cartesian equation of the above curve. Well, since r is equal to 2 cos theta, so let's put that down. Let us put that into the x and y. So we know that x is equal to r cos theta, but r is equal to 2 cos theta. So that's 2 cos theta, but that is equal to 2 cos squared theta. Now, remembering that 2 cos theta is actually the same as saying cos 2 theta plus 1. Now, and then once we move the 1 to the other side of x, what we get on this side is x minus 1 is equal to cos 2 theta. Okay. So we're going to save this. And now let's work with the y. We know that is equal to r sine theta, which is equal to 2 sine theta cos theta. And so using the half angle identity or double angle identity, this is equal to just sine 2 theta. So y is equal to 2 theta and x minus 1 is cos 2 theta. So that means if we use the equation of a circle now, or Pythagorean's identity, two theta, this is going to equal to x minus 1 squared plus y squared equal to 1. This is the equation that you should obtain, which is indeed equation of a circle of radius 1 centered at 1, 0. Okay, so that's for the first one. For the second one, let us try to sketch r is equal to 1 plus sine theta. So using the same table that we have used above, I'll just copy this much. So copy this, and I'll paste this here. Okay, let me keep this one. All right, so using the same thetas, if we put it into the r column, what we should get is the following. So we should get 1 plus root 2 divided by 2, 2, 1 plus root 2 divided by 2, 1, 1 minus root 2 divided by 2, 0. Then 1 minus root 2 divided by 2, and then back to 1. So that's for the r. For the x, we substituted to r cos theta, which is going to be given by 1 root 2 divided by 2 plus 1/2, 0. Negative root 2 divided by 2 minus 1/2, 0, negative 1. Negative root 2 divided by 2 plus 1/2, 0. Root 2 divided by 2 minus 1/2, and 1. And then for the y1, what we should get is 0, root 2 divided by 2 plus 1/2, 2. Root 2 divided by 2 plus 1/2, 0. Negative root 2 divided by 2 plus 1/2, 0. Negative root 2 divided by 2 plus 1/2, and then back to 0. So if we try to plot this on the graph, let's see what we can get. So this is the x-axis. This is the y-axis. Okay, so let's say we go this being 1, This is 2, -1, -2, and then 1, 2. So what this should look like, so we have a point at 1, we have a point at 0, and we have a point at 1 here as well. And then we have a point at 2 as well. So what this should look like so far is like this. And then we might have an extra point somewhere over here. And so that means it's over here as well. So this is the graph that we should get. This graph is called a cardioid. And so that's how we can sketch polar equations to on a plane. So I'll skip the finding the Cartesian equation one, or I could leave that as an exercise for you guys to try. As well, I want you guys, the viewers, to try and sketch r is equal to 2 theta and r is equal to 2 sine 2 theta. And in general, I want you guys to also observe what happens if you increase the theta inside here. So what happens with when you change it? For example, say it increases or decreases, and what kind of shape that you would get. So that's an exercise for you guys to try. So exercise. Now, there are 3 rules of symmetry in which some of them we might have talked previously. So for the first one, let us say we replace theta with negative theta. So for example, say we take cos theta, but by the evenness of the cosine function, this is also equal to negative theta, cosine negative theta. So that means we'll get symmetry in the polar axis. So that means you get symmetry in the polar axis. For the second one, if we replace r with negative r, then what we'll get is like an odd function. So say this is r, this is negative r. We have something that goes like this, but the other side is going to go like that. It's almost like an odd function. So we say that this is the symmetry about the pole. But it's like an odd function. And for the last one, if we replace theta with pi minus theta, it's like this. So if this is your angle theta, this way, pi minus theta is over here. Then we have symmetry about theta is equal to pi over 2, just this line over here. So symmetry about theta equal to pi over 2, which is like an even function. Okay, so let us have a look at some calculus of polar curves. So once again, we had a look at how to use calculus techniques to differentiate. So recall that in the previous lesson, we said that, well, dy divided by dx can also be written as dy divided by dt divided by dx divided by dt, right? So let us use our knowledge of parametric curves to determine the tangent to the curve r is equal to 2 cos theta at theta being pi over 3. Okay, so that means we have to find dy divided by dt and dx divided by dt. So remembering that, well, x here was our over here, which is 2 cos 2 theta plus 1. So that means over here, dx divided by d theta is then going to be negative 2 sine 2 theta, right? And as for the y, since we know that is equal to sine 2 theta, that means dy divided by d theta is going to be 2 cos 2 theta. Well, at theta is equal to pi over 3, we had to know what x and y are. So x at pi over 3, if we put this in, we would get 1/2. And for the y at pi over 3, oops, yeah, so cos 2 theta and then plus 1. So that's going to be 2 pi divided by 3, negative half, yep. And then so y at pi over 3, root 3 divided by 2. So that's the coordinate that we'll get. So once we have the dx and the dt, or dx divided by d theta and dy divided by theta, we could go ahead and put this in, but in place of t, we use theta. So dy divided by dx. So we put the dy first, which is 2 cosine 2 theta. Then we divide this by negative 2 sine 2 theta. And so this one here, the 2's will cancel. And what we'll get is negative cotangent of 2 theta. And once we substitute pi over 3 in, so this is dy divided by dx, evaluated as theta in pi over 3. This is going to get you 1 divided by root 3. All right. So now if we want to find the equation of the tangent, we have to put this in slope form. So remembering that, well, y minus y0, mx minus x0, where x0 is 1/2, y0 is root 3 over 2. We could just go ahead and put the values in. So that is root 3 divided by 2. This is equal to the slope, which is 1 over root 3, x minus 1 over root 3 times x0, which is 1/2. And so that means y here, 1 over root 3x minus 1 divided by 2 root 3 plus root 3 divided by 2. And that is the equation of the tangent to the curve that you should obtain. Okay, so let's continue on. Let us find the equation of the tangent of the cardioid. R is equal to 1 plus sine theta at theta being pi over 3. Let us assume that theta is between 0 and 2 pi, just to make things a bit easier for us to work with. Okay, so x here, let's have a look at x. X we know, well, r is equal to 1 plus sine theta. So that means the x is going to be 1 plus sine theta times cos theta. So that is going to be cos theta plus cos theta sine theta. Now, if we find the value at this point, so that means x at pi over 3 is going to be, so cos at pi over 3 is going to be 1/2 plus 1/2 times √3 divided by 2. So that's going to be 1/2 √3 divided by 4. As well, for the x, we will have that dx divided by d theta. This is going to equal to negative sine theta. Now I could also rewrite this as cos theta half sine theta half sine 2 theta. So that means what I'll get here is plus cos 2 theta. Yep. And so if we substitute theta being pi over 3, so dx d theta, what I'll get is negative sine pi over 3 plus cos of 2 pi divided by 3. All right. So what this should equal to is, so we have 1 cos of 2 pi divided by 3. One second. Okay, so we get 1/2 for this one, negative 1/2. And so that, okay, so that means over here, we get negative √3 divided by 2, and then minus 1/2. Right? Okay, so that's good. Okay, so next, yeah. All right, so once we have this one, how does find the y? So y, we know is going to be 1 plus sine theta multiplied by theta. This is equal to cos, so sine theta sine squared theta. And so if we find the y value at this point, so sine at pi over 3 and plus sine squared at pi divided by 3, which we know sine, so since cosine of pi over 3 is 1/2, so that means this one's going to be √3 divided by 2, then sine squared has to be 3 divided by 4. So that's going to be 2√3 plus 3 divided by 4. Okay. So that means this one is going to be 2 plus √3 divided by 4. Okay. So now finding dy divided by d theta, what we get here is cos theta plus 2 sine theta cos theta, which is exactly the same as saying cos theta plus sine 2 theta. Okay. So now over here, Did I calculate this right? Let me double check. So 2, yep. That should be right. And now we find it at pi over 3. So at pi over 3, so dy divided by d theta at theta being pi divided by 3, this should equal to 1/2 plus root 3 divided by 2. And so that means if we take the division of this value and this value, we should get that, well, dy divided by dx at theta being pi over 3 is equal to -1. So now what we want to do is to find out when the tangents are horizontal and vertical. So for the tangent equation, I'll leave that as an exercise. So for the horizontal and the vertical ones, so first let's have a look at the horizontal. The tangent is horizontal when dy divided by dx is equal to 0. So when that happens, so dy divided by dx we know is equal to the numerator. So we're going to have a look at the numerator, which is cos here. So we have that cos theta plus sine 2 theta. This is when it's equal to 0. And so that is also the same as saying cos theta times 1 plus sine 2 theta, or just sine theta, actually, 2 equal to 0. So that means we have two solutions here. So we have cos theta equal to 0, or that means cos theta here can either be pi over 2 or 3 pi over 2. But we're going to take this value up because this is actually going to be a cusp here. So it's just going to be pi over 2. As for the other solution, okay, so at 1 plus sine 2 theta, or 1 plus 2 sine theta equal to 0. So meaning that sine theta is equal to -1/2. So theta here then can either be 7 pi divided by 6 or 11 pi divided by 6. So only these three values, the pi over 2, 7 pi divided by 6, and 11 pi divided by 6 are the horizontal tangents, which we could probably see on the graph that we drew over here. It's tangent when it's over here, when it's over here, and when it's over here. But here's 3 pi divided by 2. That's going to be a cusp. So it cannot be a horizontal tangent. All right. So let us find when it's vertical now. So for the vertical one, we have to look at the denominator, which is going to be the dx divided by dt, when that is equal to 0. So when dx divided by d theta equal to 0. So since we found that, well, this is negative sine theta plus cos 2 theta, this is equal to 0. So we have to solve this equation. For this one, we know that, well, sine theta, or negative sine theta, and then changing this to cos squared theta minus sine squared theta equal to 0. Now changing to cos squared, So we have negative sine theta plus 1 minus sine squared theta. So we could remove the brackets. And that's minus sine squared equal to 0. So that means we have negative 2 sine squared. Or let me change it to the positive side. So we have 2 sine squared theta plus sine theta minus 1 equal to 0. So factoring this, we could get sine theta plus 1 to sine theta minus 1 equal to 0. So we could check each of these. So sine theta being negative 1, whenever theta is equal to pi over 2, or 3 pi divided by 2. But as we said earlier, this value is going to be a cusp. So it cannot be. It could either be horizontal or vertical. We don't know. Or it's a cusp still. So that means the other part then. So sine being 1/2. So theta being pi divided by 6 and 5 pi divided by 6 are the vertical tangents. So this part and this one over here are the values that we are looking for. Okay. So let's move on to the next subsection. So let's say we want to find the area and the length in polar curves. So let's say what is the area of a section of a circle of an arc with arc angle theta and radius r. So let's have a look at that. So we have a circle. We could break this up. Say we take from the origin to here. So that's one part. This is another part. If this is your arc, so let's call it A. We have a radius of r and an angle theta here. So what is the area of this? Well, the arc length we know is equal to r times theta. So the area of a sector of a circle would then be the fraction of a circle, so it's the arc length divided by the circumference, 2 pi r, multiply the area of the circle, pi r squared. So this one over here is the fraction of the entire circle. And this one over here is the area of a circle. Right? So we see that here, well, the r will cancel, the pi cancel. We just left with AR divided by 2. But since A is equal to r times theta, we could write this as r squared theta divided by 2. That is the arc length or area of the arc here. So this portion here. So using this formula and Riemann sums, we can determine an expression for the area of the polar curve. So for example, if we take the section that we drew earlier, oops, let me fix this one. So say we take this part and we have this curve from one point to another. Looks something like that. And we break this up into multiple parts. Say we take from here, here, and here. Each of these broken up parts has a angle of delta theta. So this part over here has a angle of delta theta. So what we could say is that we can break up the area into thin sectors. And so what our goal is here, we're going to approximate as the sectors. So because let's say, well, A1 being the area of one sector, r squared theta, well, that means the ith one, the radius is going to be the function in this case. So half times the function squared. So careful to differentiate this one. So we're using the squared instead of the double prime. So that's going to be theta I star, and we're going to multiply it by the width of the angle, which is delta theta. So that's the area of the sector. We know. So that means the ith area is going to be given by this. So the total area then would just be the limit as n approaches infinity of this entire thing. So from n I equal to 1 to n of half f squared theta I star delta theta. So that is the same as saying the integral from a to b of half f squared theta d theta, where r is going to be the function f theta, as we have mentioned a bit earlier in here, which we talked about it over here. R is equal to f theta. That's what we want to get at here. Okay, so using this formula now, let us find the area of a circle given by r is equal to 2 cos theta, which we should expect that is pi because it's the area of a circle of radius 1, but it's centered at 1, 0. So here, a to b, our interval or our bounds, are going to be the angle theta that we're interested in. So let's say that we go from theta between 0 and pi. That's what we're interested in. So area then is the integral from 0 to pi of 2 multiplied the function squared, or so 1/2 times the 2 cos theta squared and d theta. So if we evaluate this, we should get 0 to pi. That's going to be 2 cos squared theta d theta. So that's also the same as saying 0 to pi of cos 2 theta plus 1 d theta. This is equal to 0 to pi, or after we take the integral of this, we should get half sine 2 theta plus theta from 0 to pi. And the value that we should end up with, so we have half sine 2 pi plus pi minus half sine 0 minus 0. So obvious, this one should be just 0. So obviously, this one's 0, this one's 0, this one's 0. Those are gone. What we're left with is just going to be the pi, which is indeed what we wanted to obtain. All right, so let's have a look at the next one. Find the area of the region that lies inside the circle r is equal to 3 sine theta, and outside the cardioid r is equal to 1 plus sine theta. So as a visual, so say that this is your cardioid, and we have a circle that is 3, its last point is going to be 3. So say this is 3. It's going to have a circle like this. Or, you know what? Let me put this on a plane. Might be a bit easier. So we have something like this. We have a circle that has a radius of 3. And we have a cardioid that's a bit lower than that. Something like this. So what we want to find is this area over here. Okay, so first we will have to find the intersection points, which is over here and here. So find intersection. So we have to set the two functions equal. So we have 3 sine theta equal to 1 plus sine theta, being 2 sine theta equal to 1, sine theta equal to 1/2. And so that means theta is pi over 6, or 5 pi divided by 6, which is the one that we have calculated earlier. So that means what we had to integrate this. So we had to say we go from 0 to pi once again. So what that means, if our interval ranges between 0 and pi, then that means what we had to do is integrate the first bit. So we're going to go from pi over 6, or so we integrate the first part, the above function minus the lower function. So it's the integral from pi over 6, 5 pi divided by 6 of the upper function, which is half 3 sine theta squared d theta, minus the lower function, which is the cardioid, pi divided by 6, 5 pi divided by 6 of 1/2 1 plus sine theta, whole thing squared, d theta. Okay. So that's going to give you 9 divided by 2. I'll put it on the outside. The integral from pi over 6 to 5 pi divided by 6 of sine squared theta d theta, and then minus 1/2 times the integral from pi over 6 to 5 pi divided by 6 of 1 plus 2 sine theta plus sine squared theta d theta. And I'll leave it as an exercise for you guys to integrate this. It's more or less the same as what we have done before. All right. So the last part of this section is that we'll have a look at the arc length of the polar curves. So we can start with the length for parametric equations. So remembering that, well, L being the arc length is the integral from a to b of the square root of dx divided by d theta, or dt squared, plus dy divided by dt squared. Well, this is where we're going to have to use the chain rule a little bit. Well, if x is equal to r cos theta, and y is equal to r sine theta, then dx divided by d theta has to equal to dr divided by d theta and cos theta minus r sine theta. So it's a little bit of implicit differentiation as well. where r is a function of theta, we're assuming. Now dy divided by d theta would then be similar, dr d theta sine theta plus r cos theta. Okay, so let us go ahead and substitute those into the length function. So I'll just work with the square root part first. So dy divided by dx, or let me work with dx divided by dt squared. This part is going to equal to, so this is going to be dr d theta squared cos squared theta minus 2 dr divided by d theta cos theta sine theta. And plus r squared sine squared theta. And then for the other one, dy d theta squared, we get dr divided by d theta, whole thing squared. Then we get sine squared theta. And then plus 2r, there should be an r here, dr d theta cos theta sine theta plus r squared cos squared theta. Now we could just add the two terms together. So that means dx divided by dt, or d theta squared, dy divided by d theta squared is equal to, so we see that, well, if we add up and down, this will cancel with this, and we're left with the other term. So this here is just going to equal to this part over here, because cos squared plus sine squared is equal to 1. So we could just go ahead and put dr d theta squared. And then this one, same thing, we would just get the r squared, because this and this is going to equal to 1 if we add them together. So that's going to be plus r squared. So that means the length here, if we put everything back in, is the integral from a to b of the square root of dr divided by d theta squared plus r squared d theta. And there we go. That is how we can find the length of the parametric or the polar curves. All right. So that is actually where we're going to wrap things up for today. So that's the end of the chapter as well. So we finished the parametric equations and the polar coordinates. So the next section, or the next chapter that we'll have a look at, is the last chapter, and that is on sequences and series. So that's going to be for next time. It's a bit long section because we had to have a look at the sequences, we have to look at the series, and then we're going to have a look at the series test as well as a little bit of power series and the Taylor-Maclaurin series. But all that is for the next time. So if you have any questions about the polar coordinates, just feel free to let me know in the comments down below. And with that, I will see you guys in the next lesson.